some limit law, and we discovered that when a function is a polynomial function or a rational function, so when we take the limit as x approaching to a, when a is in the domain of the function, then we can just go ahead and do a direct substitution, substitute a into x to find the limit. Okay, so now what happens if the limit of the function in the denominator is equal to 0? So what happens if a is not in the domain for the function? What happens when you substitute a into the function in the denominator? You get 0 in the denominator. So for example, this is a rational function. If I do a direct substitution, substitute 1 into x over here, we're going to get 0 over 0, which is an indeterminate form to be determined. That means we don't know yet, okay? So what happened over here, we need to investigate this a little bit further in order to find this limit. So we're going to do some algebra over here. We're going to factor this numerator. To factor this numerator into x plus 1 times x minus 1. The x minus 1 here is a common factor, divide out. So leaving you with this x plus 1. Now this is a polynomial, so we can go ahead and do a direct substitution to get the limit here. So that will be equal to 2. Now notice that over here, x minus 1 is not equal to 0 yet, because as x approaching to 1, x is not exactly 1. So the x minus 1 here is not exactly equal to 0. So you're not dividing by 0, up and down, okay? Okay, the next one over here. This one here, we have two functions. This is the function x plus 1, and this function over here is the function that we just talked about here, this function. When you simplify this, reduce this, you get x plus 1. However, 1 is not in the domain of this original function right here, right? So when we reduce this function to x plus 1, we actually had to make a remark here. X cannot equal to 1, because when x equal to 1, it's going to make this original denominator here equal to 0, and that will be undefined. So this function will be equal to this when x does not equal to 1. So we know how to graph x plus 1, which is just this straight line right here. Now we have to take away when x equal to 1, because x cannot equal to 1. So over here, when x is 1, you go up and hit this point, and you make this a gap. So that will be the graph for this function over here. The difference between this function and this function here is this point right here. This here, it should be solid, there's no gap. This one here, there's a gap here when x equal to 1. Now, for these two functions, say this is the function f. This is a function f. And say this function here is a function g. Now, these two functions over here, they will agree to each other, equal to each other. When x does not equal to a, in this case, say when x does not equal to 1, they will agree, right? Every point will have the same function value, okay? Then what happened over here is when x approaching to 1 from both sides, this function here goes to say 2. And when x approaching to 1 from both sides, this function here also goes to 2. Both this function and this function will have the same limit at 1. Even though this function is not defined at 1, and this function is defined at 1, they will still have the same limit here. So this is a theme, says that if two functions agree to each other, when x does not equal to a, then both functions will have the same limit as x approaching to a, this, providing both limit exist, okay? Now, let's look at this example. We try to understand this a little bit better. So this function is a piecewise defined function. G of x equal to x plus 1 if x does not equal 1. So that will be this straight line y equal to x plus 1, but then you're going to take away when x equal to 1. So you make it a gap right here. And then the second piece is when x equals 1, the function is defined to be pi. So when x is 1 here, the function value will be pi. So it's a solid dot right here, okay? So you add a solid dot over here. So that will be the graph of this function g of x. Now to find the limit of g of x as x approaching to 1, so we go along the curve when x approaching 1 from the left side. Well, we see the function is approaching to 2, the y value going closer and closer to 2. What about on the right side? When x approaching to 1 from the right side, the function value also get closer and closer to 2. So this two-sided limit here will be equal to 2, which is the same as you do a direct substitution of 1 into this function. Because this function and this function, the difference is only this single point right here. Only the difference, because this function and this function, they agree to each other except when x equal to 1. So they will have the same limit, okay? And you can go ahead and do a direct substitution here, substitute 1 into x, then the limit here is this equal to 2, okay? Next example, when x approaching to 4 from both sides, we try to find this limit of this quotient, okay? So if we do a direct substitution, we substitute 4 into the x, both the numerator and denominator will be equal to 0. So I'm going to get 0 over 0, which is an indeterminate form. So we need to investigate this a little bit further. So first, we want to factor the numerator and denominator. So factor that. The numerator factor into x times x minus 4. The denominator factor into x plus 1 times x minus 4. Reduce it. Divide out this x minus 4. We get x over x plus 1. And notice that we're taking the limit of this right now. Now, this is a rational function, and 4 is in the domain for this rational function. So we can go ahead and substitute, do a direct substitution. So the limit will be 4 over 5. Next example, if we do a direct substitution, substitute 0 into h here, we're going to get 0 over 0, which is an indeterminate form. So we need to investigate a little bit further. So again, we want to factor the numerator. So using the different 2 square formula, remember different 2 square, a square minus b square, we factor into a plus b times a minus b. So this square subtract this square here, so will be equal to 3 plus h plus 3 times 3 plus h minus 3, which is going to be h plus 6 parenthesis times h. So that's how we got this right here. Now the denominator is h. So the h over here is going to divide out. Now that will be equal to h plus 6. So we're taking the limit of h plus 6. This is a polynomial, so we can go ahead and do a direct substitution. Substitute 0 into h, so we get 6. So this limit here is equal to 6. Now, as you can see here, this indeterminate form 0 over 0, in this case, we got a 6. Now, this is also 0 over 0 indeterminate form. The result here, we get 4 over 5. So when you get 0 over 0, do not jump into conclusion that is equal to 0 or infinity or any number, because for different example, we'll get different answer over here. You need to investigate this a little bit further. So I make a remark here. If you have a limit of a quotient, and if you do a direct substitution that gives you 0 over 0, then we will try to factor, okay, and see if you can reduce it. So over here, you can reduce out this common factor, right? Reduce it. And then you can try direct substitution again. Okay, so that is something that we observe, okay? So factor and then you reduce, and then you can try direct substitution again, okay? The next example, we're trying to find the limit of this quotient. Now, if I do a direct substitution, again, I get 0 over 0. So how can I factor this? Well, you could factor this, right? You can think about this as phi squared, and this is a square root of x. So that way I can factor that using difference of 2 square. So that would divide out this common factor and giving you the limit of parenthesis phi plus square root of x. And now you can do a direct substitution, and that will be equal to 10. Okay. Now another way to do this problem over here is try to rationalize this. You see the denominator over here? This is phi minus radical x. This is a radical sign. So we try to get rid of the radical sign here in the denominator by multiplying the conjugate of this right here. The conjugate of this is phi plus square root of x, or you say phi plus radical x, okay? So whatever you multiply down here, you need to multiply that up here. So that will also multiply phi plus radical x up here. By doing this, these two multiply will give you phi squared minus the square root of x. And you see the square side and this radical side here. Those are reverse operation, right? So they will undo and give you back the x right here. So that way, you're going to get 25 minus x in the denominator. So you have got rid of the radical sign in the denominator. Now, the numerator and denominator, you can cancel out this common factor, 25 minus x. So that will give you phi plus square root of x right here. And now you can do a direct substitution, and square root of 25 is 5. 5 plus 5 will give you 10. So the result is 10. So I'm going to make a remark here. So when you take the limit of a quotient, and if direct substitution give you 0 over 0, like this one, okay? And also, either the numerator and denominator contain this like the square root sign here, like a number or an expression plus or minus a radical, then we can try rationalize it. So you can rationalize it by times the conjugate of that, okay? And after that, you can reduce, and later do a direct substitution to find the limit, okay? Okay, the next example, we find the limit of this quotient. When we do direct substitution here, we got 0 over 0, so indeterminate form. And I notice that this time, the numerator contains this radical, minus 3. So we try to rationalize it. So we try to rationalize it, okay? To rationalize it means we try to get rid of this radical, okay? So we times the conjugate of this right here. The conjugate of this, just replace this minus sign by plus sign. And we times this up and down. Now, once you times this right here, up here you get difference of 2 square. The square of that subtract the square of this. And if you simplify it, that will become x squared. What about the denominator? The denominator, we have this x squared times this. So we just copy that down. What happened over here is the next step. Now you can reduce it. The x squared get reduced. At this point, we can do a direct substitution, substitute 0 into x. And the result here will be 1 over 6. Okay. Next example, limit of this quotient. Again, direct substitution gives you 0 over 0, which is indeterminate form. And you see this radical over here. Okay. So you're trying to rationalize it by times the conjugate. This is the difference of these two radicals. So conjugate of that will be the sum of these two radicals. So we place the minus sign here by plus, and we multiply this conjugate here up and down. Notice that this two multiply. This is like a minus b times a plus b. So that will be a squared minus b squared. So that will be the square of this, subtract the square of this, and give you 1 plus x here, and here 1 minus x here. And be very careful to put a parenthesis over here because you're subtracting this whole thing. So you're subtracting 1 minus x. Now simplify this. That will give you 2x. So we have 2x in the numerator. Down here we have x times this. So this x here is a common factor you can divide out. Now we can do a direct substitution. Substitute 0 into x right here, and that is going to give you 1 over here. So let's summarize what we have done in the example that we went over in this lesson. So for limit, if direct substitution give you 0 over 0, that is something we call an indeterminate form. We learned about two strategies today. One is try to factor that, and then you can reduce. Another strategy is try to rationalize it, either the numerator or the denominator, and then reduce. And then later you do direct substitution again. So you can try factoring or you can try rationalize. Okay. Now what happens instead of getting 0 over 0, what happens if we do a direct substitution and if it turns out to be a non-zero number over 0? For example, what happens if the numerator, when we substitute, we got 5, and the denominator is approaching 0 from the negative side? Then positive divided by negative is negative. So the limit here will be negative infinity. So the limit does not exist, but the infinite limit is negative infinity. Now, what happens if you get 5 over 0 plus? Then the infinite limit will be positive infinity. Positive divided by positive is positive. So positive infinity over here. And if you got a negative number and this go to 0, but stay negative, negative divided by negative is positive. So this will be positive infinity. And if it's a negative and then over, this is going to 0, but stay positive, negative divided by positive is negative. So this will be negative infinity. Look at example 1. This one here, we're trying to find limit of this rational function. Direct substitution here will give us 5 over 0. But does it go to 0 from the negative side, or does it go to 0 from the positive side? We don't know. Okay, let's try to investigate a little bit further and to see what happened. Okay, so the first thing we do here is we try to factor this numerator and also the denominator. After you factor this, we can divide out this common factor. That will reduce into this. If we do a direct substitution now, then we're going to get negative 1 over 0. But is it 0 minus or 0 plus? Well, let's think about it. Okay, so when x approaching negative 1 from the left side, this is going to, the numerator will go to negative 1. The denominator go to 0, but it's going to be negative because x is less than negative 1. So x plus 1 is less than 0. So it's going to stay negative. So negative divided by negative is positive. So it is positive infinity. So the left-hand limit is positive infinity. What about the right-hand limit? When x approaching negative 1 from the right side, x is greater than negative 1. So x plus 1 is positive. So the denominator go to 0, but it stay positive. The numerator go to negative 1. So negative divided by positive is negative. So that will go to negative infinity. So that is the right-hand limit. Now they don't agree. So this two-sided limit here does not exist, and there's no infinite limit either, because the infinite limit here for the left one and for the right one here, they don't agree. So no infinite limit.